Okay, now we are going to use the integral test in a family of examples that are very, very important, and they're so important they get their own name. So these are the harmonic series and the p-test. I'm treating the harmonic series slightly out of order compared to the book, just because I think it's easier to understand this way, but the harmonic series is introduced in 10.4.2, and the p-test is in section 10.4.4. Okay, so first of all, let's define what we're talking about. The harmonic series is the series of 1 over n. So this is the series 1 plus a half plus a third plus a quarter, and so on and so forth. And it's not exactly clear to me why it's called a harmonic series, but it's sufficiently important in mathematics that it gets a special name like this, of the harmonic series. Okay, so the first natural question we can ask is, does it converge or does it diverge? And so the question is, does it converge or diverge? And for this, we can go ahead and use the integral test, right? So the question is, does it converge? And so we use the integral test. With our function f of x being 1 over x. All right, we just calculate integral 1 to n of 1 over x dx. That's the natural log of n minus the natural log of 1, which is just the natural log of n. And that goes to infinity as n goes to infinity. So it diverges. Right, so the harmonic series diverges by the integral test. Okay, let's see what more we can say that's a little bit more general than that. So we'll say that a p-series looks like the sum from k equals 1 to infinity of 1 over k to the p. Right, so we can now ask the question again, what does the integral test say? But let me note for you that p equals 1 is the harmonic series. Okay, so let's figure out what that says, right? So here we're going to say f of x is going to be 1 over x to the p, or in other words, it's x to the minus p. And remember, we need this thing to be non-increasing in order to use the integral test. So let's go ahead and find its derivative. So f prime of x is going to be minus p to the x to the, right, we take a derivative, we get minus p minus 1. So this is going to be negative as long as p is positive. Right? So this is going to be less than 0 if p is positive. So let's work with that assumption. Let's assume p is greater than 0. Okay, so we assume p is greater than 0. So then we can use the integral test. So then we just need to calculate the integral from 1 to n of x to the negative p dx. Well, now that's going to be one of two things, right? So it's going to be x to the 1 minus p divided by 1 minus p, evaluated between 1 and n. if p is not equal to 1, and we will get the natural log of x evaluated from 1 to n if p equals 1. Okay, I'm going to keep both of these cases floating around. That first one we're going to get n to the 1 minus p over 1 minus p minus 1 over 1 minus p. And down here we're going to get natural log of n. Okay, under what circumstance does this expression go to 0 as n goes to infinity? Right, so that's, or not goes to 0. Well, when does that term not blow up? Right, so this one goes to infinity down here. But this one up here, this n to the 1 minus p over 1 minus p, what matters is this 1 minus p, is that a positive exponent or is it a negative exponent? Right, so that expression, this n to the 1 minus p, this goes to 0 if p is bigger than 1, and instead n to the 1 minus p goes to infinity if p is smaller than 1. So from this, we can conclude what happens to our p-series. Right, what happens to our p-series is that we have that the limit exists and is finite when p is greater than 1. The limit is infinite when we have that p is between 0 and 1. And then let me ask, what happens when we have p less than or equal to 0? Right, so that's a good exercise for you to think about. Right, the integral test does not apply in that case. But in these two cases, the integral test does apply. So I want you to think about that, and we will maybe discuss it on Tuesday, or we can bring it up at some later point. But I think that's really instructive to think about, because it uses some of the ideas we've talked about in these videos for this section 10.3 and 10.4. Okay, so from this we can draw a conclusion, which is this so-called p-test. And the p-test says that the series, right, so the conclusion of what we've said, well, I'll leave you to think about that. This says that the series k equals 1 to infinity of 1 over k to the p, so this is the p-series here on the left, that converges if and only if this exponent p is at least 1. Right, so let me give e.g. the sum from k equals 1 to infinity of 1 over k squared. That guy converges. And I'll mention a surprising fact. A surprising fact is that sum of 1 over k squared converges to pi squared over 6 of all things. So the weirdness of that limit should tell you that there's a lot of subtlety in evaluating series, because it's not at all obvious that you should end up with pi squared over 6. But for questions of convergence, we have some great tools, and we're going to work with them. And then later we will revisit these problems of how to figure out these limits, at least in some small number of situations.